Hey folks, Mr. Bullock here, and this free response AP statistics question is one that involves a chi-squared goodness of fit test. Okay, this is where we have to have the observed counts and the expected counts, and then our formula. I'll go over that in just a second. So in a hospital study of 450 patients with a particular form of cancer, the following data shows the number of these patients who survived for each given number of years. Okay, so here's my given number of years right here with 0, 1, 2, 3, 4 or more. Okay, and then over here, here's the observed number of patients that survived in those number of years. Okay, so this says test for the goodness of fit with the distribution. This is my probability distribution. I have to find this, use this probability distribution, and I don't know where they got it from. It's just something they gave to me. 2.1 to the x over x factorial. Remember, x factorial is, like 3 factorial is 3 times 2 times 1. You go all the way down to 1. 5 factorial is 5 times 4 times 3 times 2 times 1. So this is x factorial. So starts at x and then 1 less than that, 1 less than that, and so on. Okay, and then this is the number e to the negative 2.1 power. Remember, e is the number, and it's programmed in your calculators, you guys. E to the negative 2.1 power, or 2.71828. Okay, that's what E is. Okay, and this is in the context of X is the number of survival years. Okay, so what I'm going to do is use this formula to find the probability. So we need to find the expected number of patients. They gave us the observed, so we're going to use this formula to find each probability. So and then multiply each of these probabilities times the total, which was 450, to give us the expected. Okay, so in 0 years, I'm going to plug in 0 right here, 0 right there, 0 right there, and then that's going to get me the probability when x equals 0. Okay, so when I plugged in 0 right here, remember, anything to the 0 equals 1, and 0 factorial also equals 1, you guys. So does 1 factorial. 1 factorial equals 1 also. Okay, so when I plug in probability of 0, I get, this is 1 over 1 e to the negative 2.1, which is 0.122. Okay, and your E button is right above your natural log button, so your LN button. So it's right next on my TI calculator, right next to the 4. So if you just punch in second function e to the x and then plug in negative 2.1, you should get this 0.122. Okay, the probability when x equals 1 year, I just plug in 1 year right here. Okay, so 2.1 to the 1 is 2.1. 1 factorial is 1, so I get 2.1 e to the negative 2.1. And when I put that in the calculator, I get 0.257. Okay, here it is when x equals 2. I get 0.270. When x equals 3, remember 3 factorial is 3 times 2 times 1. Okay, 2 factorial is 2 times 1. Okay, and then 4 or more years, you guys. Well, 4 or more is everything else, you guys. So if these are the probabilities from 0 to 3, then 4 or more is going to be the rest of it. So it's going to be 1 minus the sum of those guys right there. So I get 0.162. Okay, so those are the probabilities. So now I'm going to multiply those probabilities times 450, the total. And this will get me each expected number of patients' survival rates for the amount of years. Okay, so if I do that, you guys, so if I multiply 0.122 times 450, I get 55. Okay, if I multiply 0.257 times 450, I get 116. Okay, so these are my expected numbers right here. Okay, so here I have, I think I put them right here. Yeah, here I have my observed numbers. Here's my expected numbers. So remember, the chi-squared goodness of fit, we're going to have our null hypotheses to be a good fit with the given distribution, so that we're going to say that they're equal, and our alternative hypotheses is that they're not equal, that it's not a good fit. Okay, so you can say that they're all equal, or you can just say they're not equal, or you can say it's a good fit. That's what goodness of fit means. It's a good fit with the given distribution, or it's not a good fit. Okay, remember our chi-squared formula goes each observed minus the expected squared over the expected. Okay, and then I do them, so I add them all up. So I'm going to do 64 minus 55, square that, and then divide it by 55. Okay, and then I'll do it again. 96 minus 116 squared and divide by 116. And then this one minus this one squared divided by 121. 88 minus 85 squared divided by 85, and so on, and keep doing that. And so that's your chi-squared. So when you get your chi-squared, I get 8.525. Okay, and since there's 5 values up here, then the degrees of freedom is 4. So if you go on your chi-squared distribution and your degrees of freedom to be 4 with the chi-squared 8.525, I get 0.074. Now in my old textbook, you guys, my old textbook, which is 15 years old, I don't get that exact 0.074, you guys. I'm looking at my textbook right now, and I'm going down to my degrees of freedom of 4, and then I'm looking for this 8.525, and then so in my book it goes from 7.78 to 9.49, and that's right in. So if I go up to the top, it's in between 10 and 5%, and this is 7%. This is in between 10 and 5%. So let's interpret that data right there. Okay, so let me get rid of that. And so with this p-value, there is some evidence at the 10% significance level, but not at the 5% significance level, because this is over 5% but less than 10, to dispute that the distribution of survival years follows the given data. Okay, so notice my old book gets me somewhere between 0.05 and 0.10. Okay, so that's just a reminder how to use your chi-square distribution. So I'd say, yeah, there is some evidence to dispute that, to say that it is not a good fit, but it's not at the 5% level. It is at the 10% level. All right, you guys, take care, everybody.